Seth's claim could be tested if the double-slit experiment were modified so that subjects were asked to consciously attempt to influence the interference pattern in real time as it builds up on the screen. In 2011, just such an experiment was conducted by Dean Radin. Because it is central to interpretations of quantum mechanics, wrote Radin, the physics literature abounds with philosophical and theoretical discussions about the QMP, including speculations about the role of consciousness. One might expect to find a correspondingly robust experimental literature testing these ideas, but it is not so, and the reason is not surprising. The notion that consciousness may be related to the formation of physical reality has come to be associated more with medieval magic and so-called New Age ideas than it is with sober science. As a result, it is safer for one's scientific career to avoid associating with such dubious topics, and subsequently rare to find experiments examining these ideas in the physics literature. Radin's experiment tested the hypothesis that consciousness could influence the collapse of the wave function in a version of the double-slit experiment using laser light instead of electrons. According to quantum theory, the interference pattern of bright and dark stripes created on a photosensitive screen should be distributed in a strictly predictable pattern, with alternating light and dark stripes of varying intensities, based on the statistical probability of a photon landing in a given spot, as computed by the algorithms of quantum mechanics. If consciousness has no effect on the collapse of the wave function, then it should be impossible for a subject to influence the distribution of the light and dark stripes in any way. Radin asked his subjects to attempt to mentally influence which slit the photons pass through by concentrating their attention on a given slit. They were asked to mentally imagine blocking one of the slits, for instance, or to mentally push the laser beam towards one slit rather than the other. If the photons responded to this mental influence, then the interference pattern would be affected accordingly. Radin's results strongly supported the hypothesis that consciousness could influence the collapse of the wave function, with a combined effect across 6 experiments of 4.4 sigma in the predicted direction. This is a very significant result, translating to odds against chance of more than 160,000 to 1. Quantum theory makes very accurate probabilistic predictions, but they are only accurate so long as no consciousness exerts an influence on them. They are like a default setting for the physical universe, describing how reality will unfold if no one interferes with it. But our beliefs and intentions do interfere, and they help to form our reality. The delayed choice, double-slit experiment. There is one other version of the double-slit experiment that deserves our attention. This version shows that conscious choices not only affect the behavior of particles in the present, but in the past as well, in defiance of our usual concepts of time and cause and effect. This will be our first encounter with another of Seth's main ideas, that consciousness is independent not only of matter, but of time as well. According to Seth, consciousness is not stuck in time like a fly in amber, but is basically free of it. It can operate within the physical universe of time and space, but does not originate in that universe, and so is not inherently bound by its constraints. In the delayed choice version of the double-slit experiment, physicist John Wheeler asked what would happen if you could wait until a single photon had already passed through the 2 slits of the original experiment, before deciding whether to keep both slits open or close one of them. Would the photon care that you had closed a slit that was already behind it? Would the pattern created on the screen be appropriate for a 1-slit or 2-slit condition? When Wheeler ran his experiment, he found that the photons would always behave in the correct manner, as though they had passed through either one or both slits, depending on the choice Wheeler had made to subsequently open or close a slit, even though they had already passed the slits. The particle would change its own past, as necessary, to satisfy the experimental setup. Our conscious choices in the present can actually affect past history. In Wheeler's words, of all the features of the act of creation that is the elementary quantum phenomenon, The most startling is that seen in the delayed choice experiment. It reaches back into the past, in apparent opposition to the normal order of time. The distance of travel in a laboratory split beam experiment might be 30 meters, and the time a tenth of a microsecond. But the distance could as well have been billions of light years, and the time billions of years. Thus, concluded Wheeler, the observing device in the here and now, according to its last-minute setting one way or the other, has an irretrievable consequence for what one has the right to say about a photon that was given out long before there was any life in the universe. Compare this with Seth's comments on the plastic nature of the past. The past is no more objective, Seth said, no more independent from the perceiver than is the present. The past itself is being continually recreated by every individual as attitudes and associations change. This is an actual recreation, and not a symbolic one. The past, again, is continually changed by you and by every individual. For basically, you see, it is not something done and finished with, as is supposed. And you are more free than you imagine to completely alter many aspects of your own past. If you say that the future is dependent upon the past, therefore, you must also say that the past is dependent upon the future. Every action changes every other action. Therefore, every action in the present affects those actions which you call the past. Ripples from a thrown stone go out in all directions. Entanglement and non-locality, the Allan aspect experiment. The last experiment we'll look at involves something called entanglement, and was originally conceived of by Einstein as a thought experiment in hopes of invalidating quantum theory. At heart, Einstein was a staunch materialist who felt that there must be something wrong with quantum theory if its predictions allowed for such a thing as action at a distance. Einstein proposed a thought experiment that he believed would invalidate quantum theory once and for all, but when it was actually carried out some 5 decades later, it was quantum theory that was vindicated, not Einstein's materialism. Particles are said to be entangled when they have interacted with each other in such a way as to become joined in a single quantum system. They are no longer individual particles, but are an inseparable whole, at least in terms of their quantum description. They are still free to move about independently, but are correlated in certain ways, so that, for instance, if one photon of an entangled pair is polarized vertically, the other will always be found to be polarized horizontally. Remember that quantum particles aren't really particles after all in the normal sense of the word. They are processes of relationships and interconnections with other processes, and entangled particles will remain in their special kind of relationship with one another, regardless of how much distance separates them. In Einstein's thought experiment, the two particles are allowed to move away from each other, an arbitrary distance at the speed of light, before an observation is made on one of them. Einstein knew that quantum theory predicted that when a measurement was made on one of the particles, thereby collapsing its wave function, the wave function of the other particle would also instantly collapse even though it was far away, much too far away for any physical signal to reach it, since such a signal would be limited by the speed of light. Not only that, but the second particle would collapse in a predictable way. If the first particle was found to be polarized vertically, then the second particle would always be polarized horizontally. Einstein believed this prediction to be a fatal flaw in quantum theory, for what could cause the second particle's wave function to collapse if no signal traveled through space to make physical contact? Remember the axiom of locality, which states that an object can only influence another through direct physical contact or through the mediation of one of the 4 physical forces, which are limited to the speed of light. Yet quantum theory predicted that entangled particles would influence each other instantly, without physical contact, and without the mediation of any of the 4 forces. This sounded like spooky action at a distance to Einstein. It violated not only locality, but his own theory of relativity, which set the cosmic speed limit at the speed of light. And if relativity was wrong on this point, it meant that there was no deterministic, objective universe, out there, in classical terms. This experiment, Einstein was sure, would prove quantum theory wrong once and for all. When Einstein proposed his thought experiment in the 1930s, physicists lacked the technical ability to carry it out. It would require a further half-century of technical development before scientists could perform the experiment, but when it was finally carried out by Alain Aspect and his team in 1981, the results were exactly as predicted by quantum theory. Quantum theory was vindicated, and it was instead materialism's axioms of locality and determinism that were shown to be flawed. Objective reality, wrote John Gribbin in his book In Search of Schrödinger's Cat, does not have any place in our fundamental description of the universe, but action at a distance does have such a place. Schrödinger himself recognized the importance of entanglement and stated, "I would not call entanglement one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought." Aspect's experiment confirmed experimentally something that physicist John Stuart Bell had already proved mathematically in 1964, that if quantum theory was correct, then there would have to be a non-local dimension of reality, which is to say a dimension of reality that lies outside of space and time. This was a crucial discovery, and Bell himself realized that a radically new worldview, a new paradigm, would be necessary to assimilate this finding. "I think it's a deep dilemma," wrote Bell, "and the resolution of it will not be trivial. It will require a substantial change in the way we look at things." Nor was Bell alone in postulating another level of reality. Physicist David Bohm also proposed a realm of existence that transcended space and time. He realized that the non-local, instantaneous connectedness of quantum particles can only be accomplished in a reality that lies outside of our space-time universe. "If this seems strange," wrote Norman Friedman, "remember that any solution will have to be literally out of this world if non-local reality and special relativity theory are both to be satisfied." Bell's theorem suggests that three-dimensional space and a fourth dimension of time are insufficient to completely explain particle interaction. An underlying reality, concluded Friedman, with a no-time attribute is required. We will encounter this no-time environment again when we look at reports of near-death experiences in Chapter 5, and again when we explore Seth's theory of reality in more detail in Chapter 6. Alain Aspect's experiment proved that there is a non-local level of reality, and, as Norman Friedman pointed out, this finding made the postulation of a level beyond space-time both necessary and acceptable. "It forces us," wrote Friedman, "to face the fact that space-time is not a closed system. A second level, at least, is in some way involved with our three-dimensional world." Physicist Henry Stapp would agree. The message of quantum non-locality, according to Stapp, is that the fundamental process of nature lies outside space-time, but generates events that can be located in space-time. String theory. We won't dive too deeply into string theory, but it is worth pointing out that string theorists, like quantum physicists, also see the need for an additional level of reality beyond space and time. Writing about string theory in his book, The Elegant Universe, physicist Brian Greene suggests that a deeper understanding of the universe will require us to dispense with our notions of space and time altogether. Einstein's theory of relativity was the first to suggest that the notions of space and time were not absolute and universal. They are not fixed and rigid, but are instead dependent upon the motion of an observer's frame of reference relative to other frames of reference. A clock, for example, will run slower if it is moving past us than if it is stationary relative to us, and the faster it moves past us, the slower it will run. As counterintuitive as this may seem, the effect is real, and if it were not taken into account, then satellite systems like the GPS network would not work properly. Because of the speed of the satellites relative to the surface of the Earth, time moves at a different rate for them, and if this were not corrected for, then within minutes, they would be reporting positions on Earth that were inaccurate by several meters.